Welcome to this video. We're going to learn how to solve problems where a block is sliding up or down a ramp. Let's start with the first simple case where it's just sliding down the ramp. There is no applied force. Gravity is what pulls the block down. The angle of the ramp is 28 degrees. We'll call that theta. What are the forces acting on our block? Well, the most obvious one is gravity. It acts at the center of the block and it pulls down. Let's assume that this is a rough surface, and so we have friction pulling the block and opposing its motion. Now, the block is sliding down the ramp in this direction, so friction is parallel to the surface in the opposite direction, like I've just shown here. The final force is the normal force. In every other case that we've dealt with, the normal force pointed straight up. But look at what's going on here. We don't have a horizontal surface. Our surface is angled. The normal force literally translates to the perpendicular force, and so it has to be drawn perpendicular to the surface. So the normal force points along this angle, perpendicular to the surface. Let's take these forces and draw them again just on a free body diagram. So I'm going to take away the ramp and everything else except just the block and its center of mass. Gravity pulls down. The normal force, kinetic friction pulls back. It's kinetic friction because the block is sliding. It's not stationary. And then the last force is the normal force. Here's what we're going to do, which is going to seem a little weird at the beginning, but you'll get used to it. We're going to act like our x and y axes are tilted. And we're going to use these tilted x and y axes to solve this problem. Doing this turns out to make the problem much easier than if we tried to use regular x and y axes. Here's the reason why. When we look at our axes that we just drew, these tilted x and y axes, we see that two forces, Fk and Fn, are already on the axes. This is an up force and this is a left force. Mg is the only force at an angle. The way it works out with geometry, and it's possible to prove this, if the ramp angle, the incline is 28 degrees, then this little angle right here is also 28 degrees. The hardest part about this problem is taking this angled force, mg, and drawing the components of mg. The components, remember, have to be parallel to the axes. So let's take a look. Here's the tilted y component. Here's the tilted x component. See how my x component is at an angle, just like my x-axis? In fact, that's the way we have to draw this x component. You might be tempted to draw the x component straight across, horizontal, but that's not right because we're not using regular x, y axes. We're using a tilted x-axis, so the components have to be tilted themselves. This is a right angle between the x and y because those two axes are perpendicular. The y component, the tilted y component, this down force, is adjacent the angle theta. So it's equal to hypotenuse cosine theta. This tilted x component is opposite our 28 degrees, so it's mg sine theta. And this is the only case in the problems we've been doing, this is the only case where the x component is gotten using sine and the y component is gotten using cosine. It's flipped. Normally, x is cosine, y is sine, but in these problems, when we have this ramp angle, it's not what we normally do, it's reversed. Now, as the block slides down the ramp, it's not accelerating down into the ramp, and it's not accelerating up off the ramp. So the net y force, the total y force, has to be 0. The acceleration, if there is any, will be down the ramp. And so that's the net x force that we look at. To the right is positive, to the left is negative. This is the only rightward pointing force. Here it is, and it points to the right. And the friction is the only leftward pointing force, so we make it negative because it's pointing to the left. Because the y forces cancel out, because there's no y force on total, the ups have to balance the downs. Fn points up, mg cos theta points down. And we can use these equations along with the kinetic friction equation, right, mu times the normal force, to solve these problems. The other thing is, once you know the net force on the x-axis, you can use Newton's second law, F net equals ma, to get the acceleration. The last situation I want to consider is where the block is not sliding down the ramp, but it's getting pushed up the ramp. Here's what I mean by that. A person is applying a big force directed up along the ramp, like this. So there's an additional force in this problem when we compare it to the last problem. What other forces are present? Well, gravity pulls down. The normal force is directed off the ramp, perpendicular to the ramp. And then friction is the last force. Friction has two requirements. It has to point the opposite way as the velocity, and it has to be parallel to the ramp. The block is going up this way, so friction has to point in the opposite direction. Have I drawn it parallel? Yes, I've satisfied that second requirement too. We can take and apply these forces on a tilted xy axis like I've shown here. So here's the center of the block, and let's draw our forces again. Gravity is down, friction pulls like this, the normal force is up off the ramp, and the applied force is along this angle. We can mark the angle theta, which is equal to this little angle here between mg and the y-axis. That's the same theta. Then we can draw components of mg. When you look at these forces, every single force is already on an axis except for mg. So mg is the only one that we have to break into its components. The y component will look like this. It lies on the y-axis. And the x component will look like this. And it's got to be perpendicular, the x component is like lying on the x-axis, right? The y component we use cosine to get because it's adjacent the angle, and the x component is opposite the angle, so we have to use sine. Like before, the total y force is 0 because the block's not accelerating off the ramp into the air or down into the ramp. And because the total y force is 0, the ups and downs balance. Up is Fn, and the down force is mg cos theta. So they're equal. On the x-axis, well, let me take that away. We've got two forces pointing to the left in the negative direction. There's friction, and then there's also mg sine theta. So both of those point down the ramp. Pointing up the ramp is this force here. So the total x force is going to be Fa is positive because it's to the right, minus mg sine theta minus Fk, the friction force. And as before, once you know the total x force, this total x force is equal to mass times acceleration. That's Newton's second law.